This video is a Thermochemistry Diploma or test prep guide. The emphasis will be a bit more on preparing you for the diploma exam, but this works just as well for unit tests you might have in thermodynamics. Specifically for the diploma, and that is for this year 2022-2023, but these weightings never really change. Thermochem is going to be a little over 20%, so you'll probably see in your grade book a similar weighting for this unit. Out of the 60 questions, that means you're going to get approximately 12 on Thermochem. So the outcomes to 20 or so are going to have to be sort of condensed into just 12 questions. There's about 12 because this is for multiple diplomas, and you also have overlap between one question might have multiple units on it. So there's two general outcomes for Thermochem. I'll go through sort of each of these outcomes and potential questions and using old release diploma 2017 and 19 questions. The first one is around interpreting chemical reactions and the energy changes. The second outcome is about the graphical version. You also always have to be aware or have developed some lab-based skills. So as a student, you should be able to formulate questions, design labs around thermochemistry, particularly some overlap with organic chemistry is likely. And you'll definitely be asked to not perform labs, but analyze lab data. You'll always have a Q is MC delta T thermochem style question. We'll see that coming up soon. The second general outcome is all about, as mentioned a second ago, the difference between sort of the reactants and products in a graphical version. So there's just four general outcomes, four specific outcomes for this general outcome. So you have your reactants and products, and it's all about this middle, what's going on between the reactants and products. If you add a catalyst, what's this barrier called? Bond breaking, forming, endo-exothermic type terms. So we'll get into those in the later part of this video. So looking at some examples and details of the general outcome 1, I've pulled two outcomes, 1.1 and 1.8. You have to remember Q is MC delta T from Science 10. Most students have sort of forgotten that from grade 10, and you have to get a reminder in Chem 30. And here's a fairly typical thermochem experiment. Again, this is a question from one of the released items. So typical on an exam, you get the actual question at the bottom. So don't read through all the details. What is the experimental molar enthalpy of reaction for glucose? You need that chemical. So we're going to need the change in enthalpy, and we're going to need the amount of moles that released that energy. And that's why, paying attention to the chemical is sometimes very crucial. In this case, there's sort of really just one mentioned. You just have to realize that this enzyme is not something that reacted. So you can get enthalpy change from Q is MC delta T. Again, calorimetry will be on every diploma. Sometimes the energy that's released or absorbed will just go into water, and sometimes you'll have it go into a water and a can in a combustion reaction. If whatever surrounding details you're given, you must use. So Q in this case is 100.0 milliliters, would be equivalent to grams. This is going into water. It's very common on diplomas now to have a non-water surroundings to make sure students just don't always use 4.19 joules per gram per degree Celsius, and your delta T is 10.1. So that gives you the heat or the Q, and I got 4,232 joules or 4.232 kilojoules. So that gives us our data we need to get our enthalpy change. We've got our energy, and this is a warming up. The final temperature is hotter, so it would have a negative enthalpy change. Then we just need our moles. And the only thing really to watch out in this question is making sure you're just using glucose as mass, not a catalyst. An enzyme would be a catalyst. That's not used. It's not what's reacting. Don't include it. So we have 6.5 grams. I'm doing mass over molar mass. And the molar mass is 180.16, I believe, grams per mole. So this comes out to 36, a little over 36 millimoles. Okay. And you end up with a molar enthalpy of negative 117 kilojoules. Now in this question, whenever you see this plus minus on a test or diploma, you're not keying in that. So you'd just be keying in 117 as your answer. 2, 3 significant figures is the limiting amount. The diplomas always tell you how many significant figures. I just cut it off this graphic. So hopefully this was a fairly straightforward MC delta T type of question. I won't do any math with the surroundings, with 2 surroundings, but I'll talk about it in a later question. So definitely expect calorimetry. That's one of the 12. There is kind of this annoying outcome that you need to know that energy stored in hydrocarbons ultimately came from the sun. So anything CNH only, reading through the question is only going to distract you. This is sort of I thought more of a confusing one. In equation number 2, so that is this one, the talks about the potential energy difference. I don't want to address that, but the potential energy originally came from, if it's a hydrocarbon, don't look at the energy. Don't try to do Hess here. That can really confuse you. This is a hydrocarbon, and you need to know that all hydrocarbons ultimately had the energy come from the sun. Okay? And then you just need to deal with the other part of this question. There was a time where we'd have questions that just talked about the energy in some sort of hydrocarbon, or in this case glucose, which isn't actually a hydrocarbon, but it's close, a derivative, but that still came from the sun in photosynthesis. So no longer are the questions sort of this easy where it's direct. Typical diploma questions, one part is the sun and one part relates to endo or exo or potential or kinetic. So circle the sun. That's, again, always a small question. There's a couple outcomes around enthalpy, molar enthalpy, and in equations. Students often overthink these and they make them more difficult. In equation number 1, so we don't need to look at all the data in this question, what is the molar enthalpy of reaction? So all we need to do is set up a ratio. We need to find a enthalpy change and a corresponding moles, okay? And we need to do this for hydrogen. So we got equation number 1. We know the enthalpy change, and we want this for hydrogen, and there's 3 moles. So it's simply taking the 91.8 kilojoules and dividing it by 3 moles of hydrogen. No formation values, no need to look anything up, so you're going to get a value of a little over 30 or minus 30 kilojoules per mole. So expect this, it's on every diploma. Another example of this below, but it's the same type of thing. You just have to pull the energy term out. What's the molar enthalpy of reaction for carbon dioxide? So we've got the energy. We just have to realize this is a product. It's exothermic, so this would have a negative energy molar enthalpy, which all our answers are negative, and we have to divide it by, let's see, carbon dioxide, so 2 moles. So it looks like it's going to be D. You often don't even need calculators for solving lots of these. So expect a pretty straightforward, do you understand what molar enthalpy is, and can you pull it from some data? Okay. In theory, they could have given you a graphical version, a chemical potential energy diagram instead of an equation. It shouldn't matter. Energy out as a term outside the equation, energy in an equation, graph. Don't overthink these. The fifth outcome, use and interpret delta H notation to communicate energy changes. These are sort of using an equation or some circumstance to answer a different circumstance, typically burning a certain amount of chemical. Now, I solve these slightly different, and it will work well for this example. Instead of ever using molar enthalpy, I always tell my students, change in enthalpy over moles for any one circumstance will equal the change in enthalpy over moles for another. Okay. So you could use your equation data to fill in one ratio, and then you could solve this ratio if you're told you burn 10 grams or 100 joules are released. This question is a little different, but the strategy will still work. This ratio will still work for this question. What is the enthalpy change of 200 kilojoules? So something different from this equation, okay, represented by equation 2. So we have 200 kilojoules released, and we want to know what mass of CO2. So it's not moles, they switched it to mass, but this ratio is still going to work. Mass to moles for the same chemical is going to be directly proportional. If you double the moles, you double the mass. Okay? So if you double the energy, you'll need double the mass to also do that. So change in enthalpy divided by mass will equal change in enthalpy divided by mass. So in this question, using sort of our given information, we have a release of 508.6 kilojoules for some mass. Let's see, this question talks about CO2, and there's 2 CO2s. So you need to know, well, how heavy is 2 carbon monoxides? So the molar mass is about 40, I believe. A little 44. So the mass of 2 CO2s is 88.02 grams. Okay. So again, got the molar mass for CO2, and there's 2 of them, so that tells me there's 88 grams needed here for the 506 kilojoules. And then we want to solve what if 200 kilojoules is released. How heavy would that need to be? And you can solve for this. When you cross multiply, solve for that question mark, you get 34.6 grams. So this is a bit of a unique question, but what would be very typical and you would expect in all diplomas is something like this, where it's just done in moles. Okay. This question tells you or asks you how many moles are expected of CO2. And if this question was moles, it'd be 508.6 kilojoules for 2 moles. It's not a bad idea to stick in the chemical, just to remind you, equals, okay, 200 kilojoules is released for question mark moles. And this method would work too for this question, solve for the moles, and then you just have to turn it into mass. Either way. So expect some sort of question like this. This is just molar enthalpy and lets you solve a certain situation. So we know there's going to be a question about the sun. We know there's a calorimetry question or 2. We know there's going to be a simple just what's the molar enthalpy from some data, and you'll definitely have some sort of question of what is the energy or moles released in a different circumstance, and you'll compare it back to an equation. So we're well over halfway through general outcome 1. We're into sort of Hess's Law type of questions and using formation values. Predict the enthalpy change for chemical reactions using standard enthalpies of formation. So these questions should stick at they'll typically have no numbers given. If we look at this question, outside of the answer, there's no values given. So you've got to, it's a hint, you got to go to your data booklet and use the formations. And then, implicitly they're talking about formation values. So you're going to have to look up the products. So to predict the enthalpy change, you've got to sum up. So I'm just using a sum symbol of the moles times the change in molar enthalpy of formation of the products. So 2 times CO2 plus 2 times ethanol, and you're going to subtract that from the moles times the formation value you look up in your booklet for the reactants. So I'm not going to bother doing the math. Hopefully you've done this a lot in class, and that's all this question is, and you should be expecting something like this. This would be a very straightforward one. Again, this is a released item from an old diploma. You'll definitely get a Hess Law question. I'm going to go through more of a shortcut strategy for doing these. When you notice that you need to use all the equations, you don't really have to write everything out. You can just figure out what's the stoichiometric amount you need of each of the key chemicals and sort of do the math right away and not write and net and cancel everything out. So we're asked to generate this equation. And the first thing I want to notice is, do I have any extra data? And we don't here. We need to get methane, so we're going to get methane from equation 2. We need to get ammonia. That's going to come from equation 1. Hydrogen cyanide is going to come from equation 3. So it looks like we need all of these, and we're going to have to get the hydrogen to work out. But it's key that we don't have to get rid of any of these. So if I'm in a rush, I'm just going to figure out what I need to do to each of these. So if we start with ammonia, we want one of them on the reactant side, and we've got 2. So we're going to have to flip this equation, which would flip this sign, and then we have 2 of them, but we only want 1. So we're going to have to flip this, and we're going to have to divide it by 2. So if I flip that and divide it by 2, you can sort of easily write that in your booklet. You get plus 45.9 kilojoules. So it's just saving us time actually flipping it and writing everything out. For methane, that is in the right amount, but it's on the wrong side. We've got to, flip that. So when we flip this one, the number stays the same. It just becomes positive 74.6 kilojoules. So that's going to get us these chemicals on the right side, or the correct side, which is the reactant side, technically the left side. Last, we need to get our product. We need just 1 hydrogen cyanide. This has 2. So we don't need to flip this one. We just need to divide it by 2. And we get our third positive value. You really got to watch your signs. I definitely encourage you to always write in the positives and don't leave them out. So we can just add these all up. So these two are about 200 plus another 4550, so about 250. So you don't even need your calculator after doing those subtractions. The answer is going to come out to C. So if you're trying to save some time on Hess's Law and you know you don't have an extra one, you can just sort of do this. If you've got an extra equation, well then you may want to write everything out. It's going to take a bunch of time, but you will get to the correct answer if you're careful. So definitely you're going to have a Hess question. So we're pretty much up to 6 or 7 sort of guaranteed style of questions, and you can hopefully practice this from the resources your teacher's given you. Students often don't practice, and teachers, including myself, don't spend a lot of time on emphasizing you need to be familiar with photosynthesis, cellular respiration, when something is open versus closed. Those concepts sort of connect. So anything metabolic, so cellular respiration or photosynthesis, you're going to get liquid water. Photosynthesis takes energy from the sun. It's an endothermic reaction. Cellular respiration is just like open combustion, except for it happens in a cell, so you get liquid water. Open combustion, cellular respiration are both exothermic. You are going to get a question about these reactions that you understand the open, closed, and the state of the water. Now, if you flip through a whole diploma, you often have the equations right in the booklet somewhere. So if you forgot something, flip through the whole exam and hopefully you'll get a bit of a hint or reminder. So this question from a released item, which of the following statements are valid between photosynthesis and cellular respiration? So photosynthesis is exothermic. No, it requires energy from the sun. It's an endothermic reaction. So we got a wrong statement right away. Both photosynthesis and cellular respiration store energy from the sun. No, photosynthesis does, cellular respiration does not. The products in the equation for photosynthesis are the reactions in the equation for cellular respiration. That is correct. They are just, the opposite reaction to each other. So that was the correct statement. Water in the photosynthesis reaction is in the liquid form. That's true. That's in a cell. While the water in cellular respiration is gaseous, no, it would also be in the liquid form. So lots of little true and false bits, but only C is totally true. Please make sure you go through these reactions and you're familiar with this. It can be a fairly straightforward question if you have fully prepared for it. So now we're into general outcome 2. Generally, students do much better in general outcome 2. It's not as challenging. It's very graphical. So you have to be aware that activation energy is a barrier that's always there for all chemical reactions. So that barrier, if you look at your reactants, is up to the very top. This is your energy of activation. It has to be positive. It's always there. Even in an exothermic reaction, it doesn't just happen on its own. Your wooden desks, if you have them, don't just burst into flames. You have to provide some heat or energy to get it started. So that would be the activation energy for the forward reaction. We'll talk about reverse maybe shortly. So the correct statement from the following diagram, that the diagram is exothermic and would require energy input to start it. This is an endothermic one, so those are out. And so it is endothermic and would require energy to start it. You always have to put energy in, so that's what this question is getting at. There is always a barrier. Don't think because something is exothermic, it just happens all on its own. So that's sort of the first outcome, activation energy of the first specific outcome for outcome 2. Second one, explain that energy changes that occur in chemical reactions refer to bond breaking and forming. This doesn't typically go well. Students don't sort of fully connect the bond breaking and forming to these chemical potential energy diagrams. So we got reactants, we got products. Bond breaking is pulling things apart. Imagine you had hydrogen gas and iodine gas, and you're going to react them and you got to pull them apart. The H's have to be separated, the I's have to be separated. This, what we called activation energy before, but this going up is bond breaking. I'm going to use BB for that. The first part, the going up, the activation energy is breaking bonds. So the up is bond breaking. The down is when these are apart and they come back together in a new combination. So the down is the bond forming. And it's always like this. This is crazy oversimplified. Reactions don't often happen in just sort of one step, but for Chem 30 they do. The up is the bond breaking, the down is bond forming. It's always energy being put in the bond breaking, and you always get energy coming out in the bond forming. In this particular example, this graph, the energy that needs to be put in to break the bonds is greater than the energy you get back. So net, this is a endothermic reaction where delta H is greater than 0. There's more potential energy at the end. We didn't get as much out. So bond breaking, up, bond forming, coming down. The changes in potential and kinetic are kind of different. It's the same outcome, but you have to kind of separate things. So this whole graph is potential energy. This is the difference. Bond energy had to be put in to break the bonds. Potential energy put in. Some potential energy was released in the bond forming. So we have a difference in potential energy. So I'm going to relabel this. Potential went up. We have the law of conservation of energy. So if we have more potential energy now, where did it come from? Well, it came from an equal decrease in energy kinetic. So we kind of talk about potential all the time in these graphs. That's the enthalpy change that you've talked about all through your course, but there's an equal and opposite kinetic energy change. Now this is what we actually measure. This is what we get when we do Q is mc delta T. Okay. And this gives us a number. Enthalpy, or Q, is actually a scalar, not a vector. You shouldn't be putting a sign to it. But this will tell us how much kinetic energy difference there was, and we equate that back to potential, and we just assume there's 100% efficiency here. Okay. So if the water cools down, okay, that means cool down, so it was endothermic, so that means there's an equal but opposite change in our potential energy. So we got these sort of equal but opposite to each other, equal in magnitude. I'm still sticking absolute value symbols around it. Big thing to emphasize here is the bond breaking and forming. Hopefully this potential kinetic swap was an important part to the start of your unit. Last outcomes around catalysts and labeling. This diagram doesn't have a catalyst on it, but what catalysts do is just give you an alternate pathway. Don't worry about how enzymes work. That's way beyond the course, but no matter what catalyst you put in, it is going to create a lower barrier. We know that the barrier is going to go above the products. Where you used to have an activation energy that was this high, we now have one that is shorter. Pardon my crooked line. Okay. And that's all you really need to know about what catalysts do, is they drop that barrier. It's key that you know that the enthalpy change is the same with a catalyst. Like, why would you use a catalyst then if the energy change is identical? Well, you get there faster. So if you're going to release 100 kilojoules and it was going to take a minute, maybe you get that 100 kilojoule release in 15 seconds. Often it can be orders of magnitude faster, but no change in delta H. Now, rate of reaction is not something studied in regular 30, so it's just not a topic you have a lot of experience with. Advanced placement students would have spent a whole unit in high school on rates, but not most students. Last, the Alberta Ed Bulletin for Chemistry has some comments about trends in student performance and common errors. So I just want to highlight some of those fairly quickly and make sure that you are aware of these common errors, and hopefully your teacher prepared you well and you can sort of emphasize these pieces even more than your teacher might have in the limited time they might have had to get through this unit. So there's a warning. Some students just always use the specific heat capacity of water, and most diplomas now will have a question where the heat goes into maybe a block of aluminum or a block of iron. We definitely put this on our unit tests in my school. So make sure you're reading the question, and if the energy isn't going into water and you have to do MC delta T, you look up on page 3 of your data booklet. There's iron, aluminum, tin, I know water, and probably a couple others that they could ask. Second comment they have, or that I'm highlighting, is just being aware of that liquid water we talked about. You need to be aware of photosynthesis, cellular respiration. It is going to be a question. Make sure you prepare for it. And then last, I'll highlight this bond breaking forming is a concern they have in the trends for student performance. So make sure you realize the bond breaking is the up part, exactly the same as activation energy. Bond forming is the going down, the release. So in and out. You always have to break bonds first going up, and then you get new bonds formed. If you don't break bonds and form new ones, it's not a chemical reaction, and that's not what we're studying chemical reactions in this unit. few other specific details. Students should definitely be familiar with multiple designs of calorimeters. Back a decade ago, I was a little guilty of just sort of focusing on your styrofoam cup calorimeters, where Q is a lot simpler. It's just MC delta T of the water. You could ignore the styrofoam. Combustion shows up in diplomas almost all the time. There's so many design problems, efficiency problems of losing energy coming out the sides. But I want to particularly emphasize that you might have to do a Q total with this design. You might have to do Q of the water. And if they give you the data for this metal can, you'd have to include that. Now, often it's aluminum. In the labs we do in my school, we just use aluminum cans and the students can weigh them. And we're going to assume that the delta T of the water is the same as the delta T of the metal. Okay, if you let them equilibrate, they should go to the same delta T. So 2 setups, make sure you can do calorimetry experiments with both. One of the assumptions you have to make in calorimetry for solutions that are dilute is just using the solvents. If you have 0.100 moles per liter of HCl and you've got 27.5 mils of this, okay, it's talking about using just the solvent for doing your calculations. So we'd assume this is mostly water, so pretty close to 27.5 grams of water. And you'd use the specific heat capacity of water. You've maybe been doing this and not even realizing you've been doing it with dilute aqueous solutions. Everybody does an acid-base neutralization in calorimetry, typically the start of a course. The comment again, I'm just open versus closed, and water vapor being a product or reactant. It's been in the bulletin twice. It's an outcome. Make sure you know it. They just give an example of some of the chemical potential energy diagrams. Even though you've learned about activation energies and barriers, you might see them without this barrier in front, and that's fine. That's something that they'll do. Okay. I mentioned a little bit ago with the 2 designs of calorimeters, the styrofoam cup efficiency is pretty close to 100. This setup can easily be 30% inefficient or 30% error. Lots of heat can go out the side depending on the heat shield you have and the setup and how well you have your heat source or your combustion reaction close to the can. So you should be able to calculate an efficiency. So make sure you have done that. You're comparing the actual energy release to the theoretical value, and you should expect your efficiency to be much less than 100. Okay, this goes back to that design type outcomes that I mentioned, and this is the most likely sort of application of the design outcomes that you might see on the diploma exam. Your teacher would have had to have covered some of these planning and performing and recording outcomes, but your diploma can kind of hit on it theoretically with efficiency. I mentioned don't worry about the types of catalysts and enzymes. Just any catalyst, regardless of the type, has the same effect, and don't put time into studying different enzymes and how they work, platinum versus biological ones. It doesn't matter. Enzymes are enzymes for the sake of Chemistry 30. So that is the end of this video. I know it was a bit long, but if you sort of heed my comments, you realize there's only 12 questions, you go through and you start guessing the 12, you should guess the context of almost all 12, or at least most of them. You just don't know what nuances they're going to do. And if you're writing a unit test, you would expect, all these outcomes to show up somewhere on your unit test, and a bunch of them are going to show up repeatedly on a unit test, like molar enthalpy and communicating enthalpy with the diagrams or the term outside or the energy term inside. Okay, you might get more than one Hess question, but on your diploma, you're not going to see any repetition of these individual outcomes. So good luck on your upcoming assessment. If you do like this video, please consider subscribing. Over time, I will put up diploma prep videos for all 4 Chem 30 units.